Alright, in this video I'll be proving de Moivre's theorem, and basically it's one of the more interesting proofs in complex analysis, I think. And basically de Moivre's theorem, like I said in the previous video, is probably one of the most useful theorems in complex analysis, and so I'm just going to get right into the proof of it. So I'm going to prove it using power series expansions. There is another way, there are actually several other ways to do it, but I'm just going to do it this way, because this way makes the most sense to me. And I can explain this one the best. So basically, if you remember that if you take the power series of e to the x, it's just k goes from 0 to infinity, x to the k over k factorial. And it turns out this can also be written as e to the z, well I should say in complex, if you replace the x with a z, the power series is exactly the same. So really it's just k goes from 0 to infinity of z to the k over k factorial. You see the only difference in the complex version is that we replace the x with the z. It's pretty much the same thing. Except now we're working with complex numbers, not just real numbers. So, and remember for sine of x, the power series is k goes from 0 to infinity of negative 1 to the k x to the 2k plus 1 over 2k plus 1 factorial. And for cosine of x, it's just k goes from 0 to infinity of negative 1 to the k over x to the 2k over 2k factorial. And if you remember that the negative 1 to the k is because the signs alternate for the power series, so you're going to have a minus plus for each term. And so basically I'm going to prove that e to the I theta equals cosine theta plus I sine theta. Of course, you know, this is nice to say that this is correct, but of course proving a theorem is a lot more difficult than simply saying this is probably what it is. Anyway, so I'm just going to go ahead and expand out. I'm going to start by expanding out e to the z. E to the z, like I said, was just k goes from 0 to infinity of z to the k over k factorial. So we're just going to end up getting 1 plus z squared over 2 factorial plus z cubed over 3 factorial, so on and so forth. And that's pretty much all that's, like I said, the expansion is just like for the real, for e to the x, except now we're just replacing x with a z. And we can put in any complex number we want in here, and this would be a valid expansion. But anyway, so that's the expansion for e to the z. Now for sine of x, for the sine part, I should just say it's for sine theta. For this part, I'm actually going to replace the theta with a z, and I'm only going to do this for sine. So I'm going to say that sine of z is just going to be equal to k goes from 0 to infinity. You know, this is kind of just, rewriting the same thing. Z to the 2k plus 1 over 2k plus 1 factorial. And of course, if you want to expand that out, you're just going to have, let's see here, 1 plus z, actually no, that is actually not right. You're going to first just have z minus z cubed factorial plus z to the 5th over 5 factorial, so on and so forth. And so basically that's the expansion for sine of z. Now, I'm going to leave like I said, I'm leaving the cosine part alone because the cosine theta you see here is just real. Here we have I sine theta, so I'm going to make use of some properties here in a minute, and you'll see why I expanded, I changed the sign from a real to a complex expansion. So I'm just going to go ahead and erase this stuff here. Obviously, the whole proof will not fit on this board, even if I wrote really small, and well, maybe if I wrote really small, then no one will be able to see it. All right, so I'm going to go ahead and erase that. So basically, we have, so for cosine, cosine of x, I'm going to skip writing the sum. I'm just going to go to z, actually, I'm going to go with a 1 plus z squared over 2 factorial minus z to the 4th over 4 factorial plus z to the 6th over 6 factorial. I think I may have actually switched the order of my signs here. Let me check this for a second. So here, so it should be minus plus minus. Yeah, like I said, these expansions, sometimes they can be a little annoying because you have to keep track of all your signs. And actually this should of course be an x, not a z. X, so x. Okay, so that's cosine. Now for sine, here's something interesting about the sine. If I replace the z with I theta, I'm going to have I theta minus I theta cubed over 3 factorial plus I theta to the 5th over 5 factorial minus I theta to the 7th over 7 factorial, so on and so forth. Now, here's where the properties of imaginary numbers become incredibly useful. So basically, keep in mind that I can always factor out this I. I can always factor out this I out of each of these thetas, and but before I even do that, I'm going to actually just write it as I theta. Actually, I can even get rid of the parentheses. And so here we're going to have minus I theta cubed over 3 factorial plus I to the 5th over theta to the 5th 5 factorial, and then of course minus I to the 7th theta to the 7th over 7 factorial, and so on. Now, an interesting property of complex numbers is that if you have I squared equals -1, this one I already talked about, I cubed is equal to -I, and then I to the 4th is equal to 1. And that is, this right here is very important. So what we're going to do is basically, we're going to essentially replace this I cubed with -I. And remember that if you have so I'm going to actually just write it down here. So I theta, and so I cubed becomes -I, and I can pull that out. So I can have minus a -I times theta cubed over 3 factorial. And then for I to the 5th is actually just the same thing as I. And so I can just have I times theta to the 5th over 5 factorial. And then here for I to the 7th, this is going to be like I to the 3rd. So I'm going to have, again, it's going to be minus a -I theta to the 7th over 7 factorial. And you can see this pattern repeats indefinitely. So if you have 2 here, it's going to be -1 if it's divisible. But if your number up here is divisible by 2, you're going to have -1. And if it's by 4, you're going to have 1. And by 3, you're going to have -I. Essentially, it kind of loops around. I'm probably not explaining it the best way possible, but this is kind of the idea. Remember, I is of course equal to I. Then you have -1, -I, 1, and then it repeats back and forth over and over again. And this is exactly the same thing here. So we're going to have this exact same, we have the same pattern over and over again, where we have I plus I plus I, or yeah, plus I plus I plus I, and this always turns into positives because -I becomes just plus I, and then this I right here is already positive, and again here you have -I, that again just becomes positive. So all these terms, really, there's all the minuses, they drop out, they becomes just positive. So I can just now get rid of this. I'm just going to basically do the exact same thing. I'm going to write it just a little bit neater. So here, like I said, getting rid of all this, I'm just going to go ahead and skip to the part where I factor the i's out. So I theta, and then we have plus, remember, plus I, because -I cubed is just plus I, times theta cubed over 3 factorial. Then we have plus I times theta to the 5th over 5 factorial, so on and so forth. And remember, the only trick here is that you have to remember that I squared is equal to -1, I cubed is equal to -I. That's all there is to that. And as long as you're careful with your signs, you'll see that this is what you're supposed to get. And so really, what you can do now is, since I is multiplying all of these terms, all you really can do is just factor out the I. And you're be left with theta plus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, so on and so forth. And if you remember that if I just had sine of theta, that's just equal to this. This is the power series expansion of sine of theta. And all I'm doing now is I'm factoring out the I and multiplying by that. So as you can see, we now have established the I sine theta. Now we know I sine theta is in a power series expansion. So I'm just going to go ahead and now put it all together. We're pretty much done. We're almost done. Just going to go ahead and erase this stuff. This proof does take a little bit of practice and a little bit of pretty much a little bit of practice to kind of get used to all the stuff that's going on. But it's pretty intuitive once you do see it a few times, once you practice it enough. Alright, so basically, I'm just going to go ahead and now write out what we're trying to prove again. So e to the I theta equals cosine theta plus I sine theta. And remember that we established that sine theta is just equal to I times theta plus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, so on and so forth. This is this. Now for the cosine, it's very similar. Remember, for the cosine of theta, we're essentially just going to have 1 plus theta squared over 2 factorial plus theta cubed over 3 factorial. So, no, my bad, guys. It should be this. It should be minus, plus, and then, let me see, yeah, it should be minus, plus, so on and so forth. This should be 4 factorial, and this should be minus 6, whatever. So this is a shorthanded version of the expansion. Now, I already showed what e to the z looks like, because and remember, we can just replace that z with I theta, and you'll see the powers. I'll just go ahead and now write everything out, just so it's all clear. So for e to the I theta, we're going to get, you can go ahead and even erase this part. So for e to the I theta, we're going to have 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial, so on and so forth. Should probably write that out. And that's going to be equal to cosine of theta, which is going to be 1 plus theta squared over 2 factorial plus theta to the 4th over 4 factorial. Again, I'm messing up my signs, but anyways, and then so on and so forth. And I'm going to go ahead and write the sign underneath it. So I times theta cubed over 3 factorial plus theta to the 5th over 5 factorial, so on and so forth. It's getting cumbersome to write everything out. And of course, there should be a theta term here. But anyway, so as you can see, these expressions are equal. They're essentially they're equal, because if you take all this stuff and combine it with this, you're going to have e to the I theta. And so really that's essentially how the proof works. Now, here I have a minus sign, and for each alternating term I have a minus sign. But remember, if you have the e to the I theta, remember that the minus terms drop out. They drop out of each of these. For the cosine parts, like for example, this is a cosine part, that's a cosine part, because they're even powers. The minus sign also drops out, because you have I squared equals -1, so a -1 times a -1 just gives you 1. And so that's why this is positive for each term. Here it's minus plus minus, but I squared is equal to -1, and I to the 4th is equal to 1. So essentially the cosine terms also become positive. And because they're all positive, you see that e to the I theta, which is always positive, is just equal to this. And lo and behold, that is essentially the proof. And there's a lot of stuff in this proof, and it's kind of hard to kind of even organize what the best way to show this proof is, but hopefully you understood at least some of it. If you practice it a few times, you'll be able to understand a little bit better. That's essentially the proof. And so the next video will not be as complicated as this. I'm actually going to get into functions of complex numbers, and I will not be doing too many proofs until actually later on in the series. I just kind of wanted to show what the proof of Moivre's theorem is, because I think it's very interesting. But anyway, so I hope you guys enjoyed, and I'll see you guys in the next video.